Okay, let's take a look at how to do these questions from chapter 8. Once again, I'm just going to get you started, and then you're going to be on your own from there. So these are conceptual questions. This first one is a potential energy versus position graph. And so here is a particle moving on an x-axis, I suppose, and we've got these different regions. A says rank the regions according to the magnitude of the force on the particle, greatest first. Well, remember, what we had seen in the reading, which hopefully you've done the reading, is that, there we go, the force is the negative derivative of the potential energy with respect to position. So it's really just the slope. So the force is the slope. Slope. The force is the slope. So you can go from there and figure that out, just looking at the slopes. What value must the mechanical energy, Emech, of the particle not exceed if the particle is to be trapped in the potential well at the left? I think it's pretty easy to see that if you're going to be trapped in this potential well, that how much energy, the maximum amount of energy you can see is going to be over here. So take a look once again back at the reading and look at these potential energy graphs and turning points and equilibrium points and things like that. So just making sure we're looking at these pictures right here and how much mechanical energy it's going to have in total. You should be able to answer those. And trapped in the potential well at the right, and able to move between the two potential wells, but not to the point H, so not past the point H, so kind of stuck in the middle here. For the situation of D, so D is able to move all the way. And which regions of BC, so this region, DE, and FG, will the particle have the greatest kinetic energy and the least speed? So the greatest kinetic energy is going to be where you have the least amount of potential energy. So just kind of maybe a general reminder of this whole thing is that your mechanical energy is going to be your potential energy plus your kinetic energy, and this is going to stay constant. So if you've got less potential energy, you'll have more kinetic energy. And the speed is related to the kinetic energy. Okay, so there's that one. Once again, I didn't answer it, but hopefully that got you going a little bit. So this one, figure 820, shows 1 direct path and 4 indirect paths from I to F. Along the path and 3 of the indirect paths, only a conservative force acts. Along the 4th indirect path, which we don't know which one it is, both the conservative and a non-conservative force act on the object. The change in mechanical energy of the objects, the change in the object's mechanical energy going from I to F is indicated along each straight line segment of the indirect paths. What is the change in mechanical energy from I to F along the direct path and due to the non-conservative force along the other path? Okay, so for this one, you're just really starting to add things up. So let's just start with this top path right here. So we're adding 32 joules, and we're subtracting 30, and then we're adding 10. So along this path right here, what's that give us? 32, 12, so that's just plus 12 joules along this path. Let's go along this path right here. So that's plus 20 minus 6 minus 4. So this path here had plus 10 joules. Okay, so that's interesting. Those are different. Let's do this one. That's plus 15, plus 7, 22. So along this path is also a plus 12. I'm suspecting the bottom one's going to be plus 12 too. 40, 32, yeah. So this is also plus 12 joules. So along this path, there was a non-conservative force that acted that stole away 2 extra joules. So we know going from here to here should take 12 joules. And due to the non-conservative force, we're losing 2 joules along the non-conservative force. So the change in mechanical energy is going to be 2 joules. So that's it. Okay. Righty. Number 4, a small, initially stationary block released on a frictionless ramp, height of 3 meters. The heights of the ramps are shown. Which hill is the first hill the block cannot cross? Okay, just use your intuition here. I mean, if it starts up this high, it's not going to get any higher than this as long as there's no friction. It's a frictionless ramp. What does the block do after failing to cross that hill? Well, it can only go up here. It's going to go back, and it's going to go back, and it's going to go back, right? Just like the energy skate park with no friction. Of the hills the block can cross, which hilltop is the centripetal acceleration of the block the greatest and the normal force the least? So the greatest centripetal acceleration is when, assuming that these are all the same shape, is when your velocity is going to be the highest. And your velocity is going to be the highest when your kinetic energy is the highest. So just use your intuition for where the kinetic energy is the highest. And the normal force on the block is the least, is also the same spot where the kinetic energy is the highest. I guess I just answered it for you, but because I pointed. Okay, in this one here, we slide from A to C along a frictionless ramp, and then it passes through a horizontal region where friction force acts on it. Is the block's kinetic energy increasing, decreasing, or constant? Okay, but I think you can use your intuition here to tell if the kinetic energy is increasing, decreasing, or constant. Is the block's mechanical energy increasing, decreasing, or constant? So remember, your mechanical energy is going to be conserved if there's no friction, and if there is friction, then you can lose mechanical energy. So that's kind of just the conceptual question there. So mechanical energy is U plus K, and then you might have to add in some thermal energy that gets taken away by friction. But I think this is a pretty easy conceptual question to answer. Let's see, moving right along, number 6. Oh, this is an interesting one. Okay, so it's kind of a weird setup, but you pull upward on a rope that is attached to a cylinder on a vertical rod. Because the cylinder fits tightly on the rod, the cylinder slides along the rod with considerable friction. So you're pulling up on this cylinder right here, and there's a bunch of friction that's going to take away some energy from the system. Your force does 100 joules of work on the cylinder, rod, earth system. So this is all like one system here. An energy statement is shown in here. The kinetic energy increases by 50 joules. Gravitational potential energy increases by 20, so it speeds up and it goes up a little bit higher. The only other change in energy within the system is for the thermal energy. What's the change in thermal energy? So it's just like accounting, right? Like you add in 100, kinetic energy adds in 100, changes by 100, this adds in 20, and you're kind of figuring out the sort of difference there. You just have to consider what this change in kinetic energy really means, because it's sort of speeding up. So I don't know, just think about work as changing kinetic energy in some sense, and you'll figure out how much leftover energy or the sort of lack of energy you need to fill in this block right here. So it's just an accounting thing. I think you can probably figure it out. The arrangement is similar to question 6. Here you pull downward on the rope attached to the cylinder. Okay, as the cylinder descends, it pulls on, oh, that's clever, it pulls on another block up here via a second rope. The block slides over a table. I'm assuming there's friction here. Consider the cylinder rod earth system. Your work on the system is 200 joules, so you add in 200 joules here. The system does 60 joules of work on the block, so there's some energy sort of taken out over here. Within the system, the kinetic energy increases by 130 joules and the gravitational potential decreases. Okay, so we're just making one of these boxes down here, and then once again figuring out the change in the thermal energy. So it's just accounting. You're just seeing where all the energy went, right? So you're adding in some energy over here, you're taking out some energy over there. The kinetic energy is changing, which requires work to change the kinetic energy. So just keep track of which is adding positive work and which is adding negative work, right? Okay. So once again, didn't answer it, but hopefully that helps you. Oh yeah, keep on moving on. Here we go. If you see something like this, I think you can imagine it's going to be a fairly easy question to answer. So I'm assuming this is going to be frictionless, and that's going to have friction. So the track is frictionless except for a lower section. The block slides to a stop in a certain distance d because of friction. If we decrease h, will the block slide to a stop in a distance that's greater or less or equal than d? I think that that's pretty intuitive. It's going to have less energy, so it's going to stop in a shorter distance. I mean, I guess I just told you the answer. If we increase the mass of the block, will the stopping distance be greater, less than, or equal to d? Oh, okay, so this is actually pretty interesting. So that one you got to consider some things. For this part right here, we're just doing mgh equals 1/2 mv squared. So the mass doesn't matter. But for this block over here, for this portion over here, I think the mass is going to matter because it has a certain amount of, it has a certain mu k, a certain coefficient of friction, and the friction force is going to be mu k times the normal force, and the normal force is going to depend on the mass. Now you just have to figure out, so it's not going to be equal to, you just have to figure out whether it's greater than or less than. So I'll leave you to figure that part out. Number 9. Three situations involving a plane that is not frictionless, okay, and a block sliding along the plane. The block begins with the same speed in all three situations and slides until the kinetic friction force has stopped it. Rank the situations according to the increase in thermal energy due to the sliding greatest first. So if we're going to get more thermal energy, then we want to have friction do more work. And in one of these situations, there's going to be an increase in mechanical energy due to gravity. So one of these situations, gravity is going to add in some mechanical energy. One of these situations, gravity is going to take away mechanical energy. And one of the situations, gravity is going to do nothing. So in the situation where gravity, I'm not going to tell you which one, in the situation where gravity adds some mechanical energy, then we have to account for that as a decrease in thermal energy. So there you go. Once again, not really telling you the whole thing. Let's see, this one says three situations involving a plane that is not frictionless and a block sliding along the plane. Wait a minute, what? Oh. Hey, this is the same text for this. That's not right. Okay, sorry about that. Is the text... Oh, I pulled the wrong text for this question, so I guess we can't really answer this one. Okay, never mind, because it was the text from this question. Although that was an interesting question, maybe we should bring it up in class. Okay, one fewer question to do. Okay, when a particle moves from F to I and from I to J in the indicated directions, a conservative force, okay, does the indicated amounts of work on it. How much work is done on a particle when it moves directly from F to J? When it moves directly, oh, so it just goes directly right here. Okay, well, I think that this is pretty easy to answer as well. If we're losing 20 joules going from there to there, and we're gaining 20 joules going from there to there, the idea behind a conservative force is it's kind of independent of the path. So if this is minus 20 and this is plus 20, you can see how much the overall difference is. And then since it's a conservative force, it doesn't matter what your path is to get from there to there, the amount of work is going to be the same. So there you go. Okay, hopefully that helps you out a little bit.